Okay, that sounds like it's recording.
That was quick. We figured that out fast.
Yeah, I know. Okay, let me just arrange these Zoom things, then we can start. All right, cool. So yeah, so today's topic was going to be 2 separate workshops in the application and fundamentals series on unsupervised learning. And sort of semi-supervised learning, but we kind of decided to just combine it into one, and really the focus is pretty much just on unsupervised learning. So for those of you who are new or maybe haven't heard of unsupervised learning, like Joey Hana said, is kind of the future. I think like it underlies a lot of the methods that we already know and is fundamental to improving those methods. And it, along with maybe like reinforcement learning, are some of the most promising technologies to come to be researched in deep learning recently. So the agenda for today, unsupervised learning, as you may or may not know, is just a massive field. So this is going to try and cover just a few things that I think are a good introduction and kind of get you a good overview of what you can do with unsupervised learning. So the first thing we're going to talk about is what and why of semi and unsupervised learning. What is it and why should we care about it? We're going to talk about a class of models called autoregressive models. These are probably the most approachable in general of unsupervised methods. We're going to talk about some non-generative representation learning. We're going to touch on a little bit of contrastive learning, which I think is a really interesting area that allows for really good representations of data. And then we're going to talk at the end a little bit about like kind of a hint about what semi-supervised learning might look like. We're not really touching on it that much because it's not really the focus of the workshop, but we're going to be talking about unsupervised pre-training, which is a semi-supervised way to improve model performance on task-specific things that you might want to do. So with that, let's get into it. First thing is, what is unsupervised learning? So you've seen supervised learning, which is learning some mapping f of x from inputs x to labels y. So we may be predicting future weather data from previous weather data. We may be predicting search results from a Google query. And in general, what we get as our data set is something like this. We're learning a mapping from some well-defined input to some well-defined output, and we know that at training time. Unsupervised learning is then just learning without the labels y. And so why might we want to do that? Maybe the labels are unavailable or expensive to collect. In a lot of medical fields, for example, actually getting a label for like an image of like a lung nodule may cost a subject matter expert to have to go and spend 30 minutes of their time diagnosing a CAT scan. And that could be really, really expensive for a company trying to collect data. So you may want to try and see what you can do with just the input data and no labels. Another reason is it may just be very ambiguous what the label is. This appears in a lot of domains where maybe it's just kind of hard to assign a label, or maybe you want to try and learn something before you actually go and spend the effort to assign labels. So then what is semi-supervised learning? Semi-supervised learning is a compromise where we use both unsupervised learning and supervised learning. We're going to, in specific, discuss unsupervised pre-training in this workshop. The idea there is we train via some unsupervised objective on a large amount of unlabeled data, and then we fine-tune our model via a supervised objective on a small amount of labeled data. And I have this graph here, which kind of gets at like why this might be a valuable thing. The axes here are some sort of projection of a learned representation or a learned model of some inputs and outputs. If you don't pre-train, we see this cluster on the left. It's very spread out, very variant. In fact, the variance isn't even uniform across, and it's kind of all over the place. And that's what happens to a model trained on this specific task. I'm forgetting what the task was, but if you don't pre-train it ahead of time, this little cluster on the right, which is very uniform, very compact and put together, is what happens when you pre-train your model on what you call a pretext task. And what you get is each of these points is a neural network that was trained to convergence, and they converge to similar and near optimal points. So there's a lot of like ambiguity that is taken out by doing some sort of unsupervised pre-training. And we'll talk about in the end of the presentation some really cool results that have come out of this. But why? So unsupervised learning is the study of finding rich structure in our data. Why? Data and labels are expensive. I talked about that earlier. The medical example is a great one. Finding latent structure can reduce the effect of noise. If we enforce some sort of criterion on the latent structure that we choose to represent our data or that we learn to represent our data, we can often remove noise. I'm going to talk about denoising autoencoders as kind of an introduction to representation learning in a bit. And the whole point there is to remove noise from data so that you can maybe do some pre-process or post-processing steps down the line. It can improve model performance. And I have this citation here to a paper out of Berkeley that shows that you can actually bound the performance of hierarchical reinforcement learning by the quality of representation learned under some assumptions and some workings of what it means to be a good representation or a suboptimal agent. So read that paper if you want to learn more. It's actually pretty interesting. And finally, the manifold hypothesis, which is kind of this idea that real world data is often some latent smaller dimensional structure encoded in some high dimensional space. So on the right, I have what's commonly known as the Swiss roll data set. As you can see here, the different colors are classes, and it's really just a line that's been rolled into 2 dimensions into maybe like a Swiss roll. That's why it's called the Swiss roll data set. And you can see that we don't really need 2 dimensions. If we had like a good parametric function to project this into a single dimension, then we could just estimate all these classification boundaries as lines in this single dimension or points in this single dimension that represent thresholds. But the fact that it is, this one-dimensional data encoded in a 2-dimensional manifold makes its structure a lot more complicated and unnecessarily so. And this might be something that would throw off a model. For example, with this 2D structure, it's probably impossible without some sort of like kernelization to actually fit a linear decision boundary to most of these classes. But if we find good representations that maybe project it down to a single dimension, then we might have something better that we can work with. So it can improve model performance and simplify our representations. And how? So we talked about why unsupervised learning. The general strategy about how we go about this is in the absence of labels, we have to create our own supervisory signal. And we do this in the form of heuristics that we might say are reasonable assumptions to make about what a good representation is. And these come in a lot of forms. So there's autoregressive objectives. We're going to talk about those today. There are reconstruction objectives. We'll talk about those as well. Matching distributions. We're not really going to talk about these today. A lot of the implicit and flow models, if you're interested, take a look at, I think it's CS 294-158. They talk a lot about the more advanced side of unsupervised learning, which has to do, a lot of the methods have to do with stuff like matching distributions. Distance measures. So maybe you want to encode some data and you have some notion of what data should be close to other data in the encoding. So you can enforce some sort of distance measure. We'll talk a little bit about that today. And then another idea is like an adversarial framework. I believe, can someone correct me, or have you guys learned about GANs yet in the workshop series?
Yep.
Cool. Yeah, so you've seen GANs. So you've seen a little bit of unsupervised learning already. This is just a sample. There are many, many other methods that people have proposed. There are really niche areas of research within unsupervised learning that dive into many, many more topics than this. But the general takeaway is when we don't have labels, we need to create some sort of learning or supervisory signal by adding our own heuristics into the learning problem. Okay, so before we move on to the first class of unsupervised learning, which is autoregressive models, does anyone have any questions or comments that they'd like to make?
Yeah, what kind of heuristics can you learn? Like, for example, from your example at the hospital, right, where it's hard for a doctor to label something. What kind of heuristics can you expect to learn?
Yeah, that's a great question. I think to answer that example exactly, we'll see a few models later in the presentation that through the use of good heuristics, like, for example, I take a CAT scan of this person's lung, and then I take an X-ray of this person's lung, and I try and encode that data into some latent space of, a much smaller dimension. They should kind of look the same, right? It's the same person's lung, it's the same subject in the scan, so they should kind of look the same. And if you encode heuristics like this into your training procedure, what these models see, and I'll show the results later on, is like really highly increased data efficiency. So with maybe like 1% of the data needed, you can still achieve good performance. And we'll see that in a little bit.
Then it'll
So yeah.
and stuff. But what I want to understand is how are you mapping X to Y here without the actual Y?
Yeah, a lot of times, okay, so a lot of times you either choose some Y that you're okay with. So in autoregressive models, we're going to really kind of like make pseudo labels. It'll probably make a little bit more sense in a second, but we're going to say like, I want to predict the second half of this data point, this X, from the first half. So it gets to look at like the first half of an image and predicts the second half. So you're essentially creating your own labels or your own Y in this instance. In the case of representation learning, what you would probably do is enforce some heuristic, like I said, to learn a good representation. And then from that representation, train an actual supervised model on top of it. So unsupervised learning there is like an initial step to get you better performance in the end. Does that make sense?
That makes sense. So wait, basically what we're saying here is that it's not necessarily 100% of the time that we're actually trying to predict the direct output or the direct label.
Correct. Yeah.
Okay, okay, cool. Fine. Thank
Yeah.
you.
Any other questions? Okay. So we will get into autoregressive models. So what are autoregressive models? Autoregressive models, very generally, predict future values from previous observed values within a sequence. For example, we want to predict image pixel values from neighboring pixel values, or we predict stock prices from prices on previous days. We could predict letters in a word from previous letters, or words in a sentence from previous words. In general, an autoregressive model could be visualized something like this. So it, like in this example, we're just predicting the word right. We start off with an empty sequence. The model is fed that and it says, I might want to start this sequence with an R. The model sees that it predicted an R in the past and it says, well, what might come after an R? Maybe an I, so on and so forth. What might come after an I, a G, and then it starts to form this word right. And the thing to get out of this is the model is predicting things, and then based off of its past predictions, it's making more predictions about how to complete a sequence. So that's the high level of autoregressive models. More formally, an autoregressive model seeks to estimate the distribution of x sub t given x of all subscripts less than t. That is, it seeks to estimate the distribution of the tth data point in a sequence given all the data points before it. This can be done with a neural network, for example, an LSTM, parameterized by theta as follows. We simply say x hat, or this should be xt hat, equals the neural network when given a look at all the data that comes before t. The modeling assumptions. So this is important. The data needs to be able to be sub-indexed in some way. So we can break images into pixels, we can break sentences into words, but other data may be harder to break up and define an ordering for in specific. So you might think to yourself, okay, we can sub-index pixels out of an image, but how do we actually define an ordering? Which are the first T's? A typical thing to do is what's called a raster scan or a raster scan order, in which you kind of like you're reading left to right, up to down. So you predict the first pixel in the top left, the one to its right, the one to its right, and when you finish a row, you move on to the next row. But regardless, if you're going to build an autoregressive model, the data has to be able to be sub-indexed. Another modeling assumption is, of course, that sub-indices have dependencies between them that allow for modeling. And of course, this is a modeling assumption of machine learning in general, is that your inputs and outputs have dependence. But this is actually like a non-trivial assumption in a lot of cases. So it's worth calling out. Okay, so now that we kind of get the setup of autoregressive models, they're taking previous decisions and using those to predict future decisions. Let's talk about how you might use this for generating images. So the first model I'm going to introduce is called Pixel CNN. The problem it's trying to solve is modeling the distribution of natural images, and it's going to do so by predicting pixel by pixel the values at images. So Pixel CNN models images as a sequence of pixels where pixels to the left and above come first, like reading order. This is called a raster scan order. Pixel CNN's network predicts a distribution over RGB values for each pixel given those behind it in the defined order. So given those to the left of it and above it, it will predict the next pixel. And you can see here it kind of snakes over the predicted image, going all the way from the top left to the bottom right. And at each pixel, it sees all these values in blue here and outputs a distribution of what the RGB value might be at that pixel location. What we have here on the right is kind of, if you want to make this faster, you might implement it kind of like a convolution operation. And what you need to do here is define some sort of masking so that the pixel can't be trained to look ahead of it. So we can do some sort of convolution operation, but we need to make sure that all the values of the actual pixels ahead of it are masked. So they have values set to 0, essentially, so that when we're training to predict x sub I, we can never look at x sub I plus 1, or the operation zeroes it out, so it's almost as if we aren't looking at it. Does that make sense to everyone? Any questions about this so far? Okay. And then, so Pixel CNN works okay. Its results are pretty good, but maybe a better solution is in the second paper called Pixel Snail. So Pixel CNNs use convolutions to represent the kind of context that the model sees. And that's fine, but you can imagine a convolution may have a hard time reaching context really far back in the input. I have this image that wasn't supposed to pop up yet in the slide, but you can see the receptive field that this pixel in yellow gets to look at when being predicted. So it's really not looking at the whole image that came behind it. It's only looking at a subset of it. So Pixel Snail, which is an improvement on Pixel CNN, attaches an attention mechanism. So you guys remember from last week, we talked about attention mechanisms. And it attaches an attention mechanism to the convolution to allow the model to attend to longer dependencies, long-range dependencies in previous pixels. And what you see here on the right is the receptive field of a Pixel Snail prediction. So we can look all the way back at the entire image and attend to each of these values. The values in kind of the dark purplish are the ones whose essentially like they assign some importance score that had to do with the gradient back into that pixel. These are the ones that exceeded some threshold. So Pixel Snail is looking at a lot more of the images, and the results they get are a lot better. And here you can see on the left a little bit of the architecture about what Pixel Snail looks like. So essentially, it's the same deal as before on the left-hand side. We get a residual block, which is just residual connections and a few convolutional layers. But we also have on the right side this whole flow of attention. And the attention that we're looking at here is the same key value store that I talked about last week. So we have the Q, K, and V matrices, and we do the scaled dot product attention here to actually attend to all the inputs that come before this pixel in the pixel snail input. And you can kind of visualize what this looks like. It's like a snail. That's why it's called, or that's one way to think about it, is it's like a snail crawling along the image, predicting each pixel as it goes along, looking at what it's seen before. And here are some of the results. They're very small, so it may be a little bit hard to see, but I'll send out the slides later and maybe you can zoom in and take a look. They're pretty realistic looking. It does a pretty good job of modeling the distribution of images. Yeah, I don't know if you can see any of these, but you see a lot of like animals popping up. You see a lot of like realistic looking backgrounds. Some of them have clouds. Animals, I think that might be a car right there. In general, it does a pretty good job is the point here. So any questions about Pixel Snail or Pixel CNN?
I'm trying to understand how the attention mechanism thing works. So is it possible that the attention mechanism, what does the attention mechanism take in the first place? I'm really confused about it.
Yeah. So this is a good point. The attention mechanism takes in different things, whether you're training or whether you're doing training or inference. Okay, so this is pretty important. During training, it takes in the actual pixel values. So you'll feed it an image, or you'll train it on like a set of images that you want it to represent. If I'm predicting this yellow pixel, what it gets to see is the actual values of the pixels behind that in the image. So let's say I fed it, or I'm training on like an image of a cat, and I'm at this yellow pixel. It will get as input some sort of encoding via like convolutional layers of all these pixels to the left and above this yellow pixel of the cat. So maybe it sees the face of the cat, it sees the fur and some of the background. The attention mechanism, like I said, gets the encoding of those pixels by a convolutional layer or a couple convolutional layers. And the actual parts of the attention mechanism, like the Q, K, and V matrices, will be the features of that encoding from the convolutional layers. So it's the features of the convolutional encodings of all the pixels that precede the pixel being predicted. That's what the attention mechanism sees. Is that clear?
Yeah, cool. That makes sense. Thank you.
And then, so I said that that's what it sees at training. That's what we call teacher forcing. So it's saying no matter what you predicted beforehand, we're going to tell you what it actually should have been so that you can learn based on good looking data that came before. But at inference time, obviously, you don't have access to what the true image that has been generated should be. So you no longer teacher force and you just feed it its own predictions that it predicted for previous pixels. Does that make sense?
Yeah, that makes sense.
Any other questions? Cool. Okay, so Pixel Snail does a pretty good job. It represents the distribution of natural images really well, but that's not where we have to stop. WaveNet is an approach that applies the autoregressive modeling principle to audio waveforms, and it uses something called dilated convolutions. I've linked both the papers to WaveNet and a paper introducing dilated convolutions here. The idea here is that dilated convolutions kind of space out where they're looking at. So they don't look at every pixel in like a 5x5 grid. Maybe they look at pixels with space of like 2 pixels in between. And that kind of gives it a larger receptive field. That's not really important, but the meat of this is that it's an autoregressive model to predict audio waveforms from previous parts of the audio waveform. So if you're going through like, I'm not really a music person, but if you're going through like a buildup in a piece of music, it should know what happened before it in the music to kind of complete the sequence of notes. And this is a visualization, a really pretty visualization of what's actually happening here. So you can see that it gets as input the values it's predicted for the waveform before. It passes through a few hidden layers. These dilated convolutions come in, you can see the spacing between the eras as the hidden layers progress. And then it predicts the next note or the next, intensity of the audio waveform. And some of the results, let me know if you guys can hear this. Can you hear that?
Yeah, I think you need to turn it up a little louder.
Yeah.
Oh, crap.
Pretty dim.
Okay, I'm gonna take off my headphones. This doesn't kill me.
Okay, can you guys hear me all right?
Yeah.
Okay.
Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
Could you guys hear that all right?
Yep.
Cool. So that was a previous method to WaveNet that didn't really use as good of modeling as WaveNet did. And we see
Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
we see the same sentence from WaveNet's model. I don't know if you guys heard that, but it sounds a lot more realistic. And this came out of Google, and this is part of why Google Assistant sounds so good when you talk to it and when you ask it questions as compared to something like Amazon's Alexa, is because they've used these autoregressive models to get a much more realistic waveform out of their predictions. One last thing, I hope you can hear this. It also makes music. I'll play this. Yeah, so it's just a quick 10-second clip. But Google showed that you could actually model complex things like music too with the same model, and just learn through the autoregression to predict future parts of the music's waveform, having only seen what came before. Okay, so that was a quick introduction to autoregressive models. There's a lot more there, and there's a lot more to explore, of course, in all of this. But are there any questions at a high level about what autoregressive models are and how you can use them?
I have a question specifically about WaveNet. You just showed us two examples of how it kind of spoke a sentence and made music. But we also talked about how we take like the past audio, right? The audio that we previously had, and then we predict what the rest of it would be. So I'm kind of confused as to what we're doing here. Is it completing a sentence over there in the model that you, in the example that you just showed us?
Yeah, so for the music, I'm not super positive on the specifics, but for the music, you can do something like you have an initial distribution, or your model emits an initial distribution of what overall music that it's seen, what the first note might look like. And from there, you just bootstrap values off of that. So you sample, okay, maybe the first note is C# or something like that. And from there, you just continue going on and on and on. For the voice, I'm not completely sure how they forced it to actually say that sentence. I guess if anyone's read the WaveNet paper, maybe they could answer. Probably a good thing to like dive in yourself and look at. But I think the point to take out of this is more the autoregressive principle of, bootstrapping off of values you've already predicted to model a distribution.
Okay, I see. Makes sense. Thank you.
Yeah. Any other questions? Okay. So if there's no more questions about autoregressive models, we're going to move into representation learning, in specific non-generative representation learning, So we're just doing predictive tasks here. We're not trying to learn any generative models. I hope when you guys learned about GANs, whoever taught that workshop talked about the difference between generative models and discriminative models, but regardless, we're not doing any generative models. Autoregressive models, interestingly, or the ones we talked about, are generative models. They learn to estimate the whole distribution of the data they're looking at by factoring it into a product of marginal distributions. If you haven't taken probability theory like CS70 before, don't worry about it. That sentence I just said may not make sense, but if you had, you can kind of think about it as predicting the probability of x1 times the probability of x2 given x1, so on and so forth. So it actually learns the whole distribution and is therefore a generative model. In contrast, the representation learning models we're going to be talking about now are non-generative. So with that, let's talk about representation learning in general. So the idea behind representation learning, or one of the ideas, is to find latent embeddings that are useful for downstream tasks. So we want to learn learnable, information-rich features. This can bring a few advantages. So it can bring data efficiency, as we'll see in a second. The DeepMind paper that I have linked achieves 84.9% accuracy using only 10% of the labeled data in the data set it's using. I'm not sure if that's ImageNet. It's been a while since I've looked at this, but regardless, they take 1/10 of the data that other papers have used and get comparable accuracy just by learning really rich features from this data ahead of time. And it can improve performance. You know, I talked about this before, but the quality of representations can lower bound performance in hierarchical RL. This paper is out of Sergey Levin's lab here at Berkeley. So with that, let's get a kind of gentle introduction to representation learning is through denoising autoencoders. And the idea here is to learn noiseless representations. So denoising autoencoders learn to remove noise from an image by projecting to a latent space and then upsampling. I'll show what this looks like as a graphical model in a second, but the latent representations are learned to be information rich and ignore input noise. So the idea is we randomly zero out parts of the input. This represents our noise. So we have a noiseless data set or practically noiseless data set, and we zero out parts of the input, which gives us noise. We pass through a model that has an encoder-decoder structure. Hopefully by now, this is kind of one of the big ideas in model architecting that you're seeing so far, is that a lot of models follow this encoder-decoder structure where they kind of squeeze the input down to some bottleneck where the size of the input at that layer is really small, and then they unsqueeze it back to something that's more interesting. And we train with a reconstruction loss. The paper talks about using maybe an L1 or L2 loss, but what they actually ended up using was the cross entropy between the uncorrupted input and the model predicted output. Here's what that looks like. So on the input side, we zero out some of the values, or in this case, maybe we're turning them white. This is the, I think, MNIST data set, handwritten digits. So we zero out some of the inputs, we pass it through the model. The model has this encoder structure that constructs a latent code and then decodes it to the output. And this prediction is kind of compared against the input before we corrupted it with all this noise. And the idea here is that the latent code should learn noiseless representations of our input. And it works pretty well. This idea has been around for a few years now. And I think there are better ways to approach this problem now, but it kind of gets at this idea of we're implicitly, or, you know, as we'll see in a few slides, we can also explicitly force things on our representations such that they behave in some way. Any questions about denoising autoencoders? Okay, so I want to step aside and talk a little bit about contrastive learning. You know, once again, there's a lot here and it's hard to cover even a big chunk of it. So I'm going to talk at a very high level. But contrastive learning is really just a way to learn a distribution. The idea comes from a more general distribution estimation technique in statistics called noise contrastive estimation. I've linked the paper in these slides. It's pretty interesting and pretty approachable as far as, mathy papers go. The idea, we want to learn representations that allow us to pick out a positive example from a list of negative or noisy examples. So if we add a bunch of noise, if we have a bunch of noise vectors and we have one vector that is the representation of some image that we've encoded, we want to be able to tell which of the vectors is the image we're looking at. We should be able to contrast it from noise, that is. Essentially, we want, this is what I said before, we want representations of our data that look different from noise. And this is really with respect to some criterion that we choose, right? I've said, like, very abstractly that we want our representations to look different, but what does that actually mean? And different papers have different approaches to what this can mean, but in general, contrastive learning tries to contrast our representation with noise. So the first example of contrastive learning that we're going to talk about is a paper called Contrastive Predictive Coding, or method. So the motivation is a representation is good if it makes downstream problems easy. That makes sense. We want representations that are useful for learning off of. The idea is that we put a contrastive loss in an autoregressive framework. Okay, so I'm kind of throwing around words that we've touched on earlier in this workshop. So what does that actually look like? Latent representations should be able to predict future latent representations. So if we, encode in some sequence of maybe words, if we encode each word one by one and then pass it through some autoregressive model, that encoding should be able to predict future words encodings as well. That might make sense with this picture. So at the bottom here, we have some waveform in blue. We can just treat this like speech, and the X's are samples of this waveform. So let's look at X sub t here. We have this encoder model, G sub enc, and the encoder model takes X sub t and through some process. If this is images, maybe it's a convolution. If it's text, maybe it's some sort of attention model or something like that. And what we get out is a z of t. This is a representation of that point in the input sequence. The idea behind contrastive predictive coding is that we also, along with this, train an autoregressive model, GAR. GAR can be something like an LSTM. I think that's what it is in this paper, actually. And what it should do is at each time step, take in the state it had before and the encoding of X sub t through the encoder, and it should produce this value C of t. And this C of t can be interpreted as a context vector. And the actual loss we impose on this is that we want C of t to be predictive towards future Z of t's. So future encodings of future points in the sequence. In this way, we kind of preserve the idea of dependence between our context and future representations. And we kind of get this idea that you can get a little bit of global information in the context that is helpful in predicting future latent vectors. Okay, so formally, we learn an encoding model to produce C. We learn an autoregressive model G to produce context vectors C from Z. And we train C of t to emit future Z values. What that looks like is if we have C of t, or what's typically done is we say that C of t should be, such a good context that we can predict K steps in the future. Maybe, once again, if this is words, we want to predict the latent representation of the T plus Kth word with just a linear map. So this W right here is just a matrix. It's essentially like linear regression here. And we want to say, like, okay, if we learn a W on C of t, it should be able to predict Z of t plus K really, really well. And what we say, and this is where the contrastive learning part comes in, is we take a bunch of other X's that aren't part of this sequence, or maybe they're part of the sequence, but not at position t plus k. And we do the same thing. And we say, okay, we want to be really close to the correct t plus k, but not so close to the other encodings of x. And this is kind of the contrastive learning idea of the other x's act as noise. We want to be able to contrast from other encodings and other encodings of other sequences, other encodings within our sequence. We want to be able to actually pick out the exact value in our sequence. And what this does is it ensures that dependence between values within our encoded sequence are really, really high. And so we get good representations that make sense globally, right? They can predict each other. And they make sense locally because they allow us to, actually encode the value. So this is quite a, mathematical and probably pretty new concept. I'm sure you guys have questions, so I'll just take a minute to stop here. Do you guys have any questions about contrastive learning or the contrastive predictive coding setup?
Yeah. So you say that we learn at the, I think this is the first like an expression that's on the page. We learn only a matrix that takes CFT and predicts CFT plus K, right? Just one matrix.
Yes.
Aren't we making a kind of assumption as to how simple the relation between CFT and CFT plus K would be?
Yeah, definitely. In specific, we're making the assumption that one can be linearly predicted from the other, right?
Yeah, we are.
Yeah, and that's that's a good thing to call out. I think the motivation here is that we want in the end these features to be so good and so information rich and so predictive that you can learn really, really simple models on top of them that do really well.
Okay.
So we're given linear regression and we can predict, future encodings of future values because our features are just that good. A lot of the tests or a lot of the benchmarks in representation learning papers like this will train some sort of representation on a data set and then see how well they can do with linear regression on top of those features. And often they do pretty well. So this is kind of, getting at this idea that like good representations should allow simple models to perform well.
I see. That makes sense. That's pretty cool. Thank you.
Yeah. Any other questions?
Wait, for contrastive learning and the autoregressive models, are these considered semi-supervised? Because like at the end of the day, like we're still using data, right? Like because I don't know, I feel like unsupervised is like you give it nothing and then it's able to learn. But with this one, we're still giving it some form of data so that it can learn. Like it's unlabeled, but like it's still data, right? So I don't know. Is there like an argument as to why it's considered unsupervised?
Yeah. So I think one thing to call out there is that in unsupervised learning, you don't give your model nothing. You give it a plethora of data. It's just that it's raw and it's unlabeled. In this example, let's take the x's to be pixels. Then this just really boils down to kind of the same thing as like pixel snail, or really the same idea that pixel snail is getting at is like, say we encoded every pixel with this G encoder. Well, then encodings of, pixel 1, 1 should be very predictive of encodings of pixel 1, 2, or neighboring pixels. So we don't actually need any labels here, right? For this to work and for this to build representations of images, I don't need to tell it like that's a picture of a dog. I can just give it a picture of a dog and it will try and predict future pixels from past pixels. Similar autoregressive idea as before. So we're just learning representations of the image that are predictive of other parts of the image. So it's almost like you're trying to learn good representations that, kind of have this idea of like what globally they fit into. That's a very high level idea, but I think that's the best way to think about, or that's the way I think about it. Is these representations encode some sort of notion of the rest of the distribution as well. Yeah, I hope I answered your question. To be clear, it's unsupervised learning because we don't actually need any labels here. We're just giving it raw unlabeled data and it's learning representations.
Okay, cool. Yeah, that makes sense.
Yeah. Other questions? And I will say it may help to like take a look at these slides or look at the paper afterwards to kind of, there's a lot of symbols thrown around here. And really like, it is kind of hard to understand at a first glance. The idea is that we construct representations that are predictive of representations of values further along in the sequence. And kind of to put this in context of why we care about this, let's say we trained this contrastive predictive coding method on a data set of 10 million unlabeled images. Now we have really good representations of natural images that are predictive of themselves in both Z of t and C of t. So you can choose to use Z of t or C of t as encodings or representations of images in the future if you want to do some sort of supervised learning task. So as we'll see in the next slide, that's exactly what they do. The idea is we build a CPC encoding and fine tune a really small model on top of these CPC encodings with a small amount of data. And the result is we get both actually data efficiency and improved performance. So right here, if we look at just the first 3 rows, this is the top 1 accuracy. Probably, I'm not sure what data set this is on, to be clear. I think it might be CFAR 100 or ImageNet. But as you can see from these labels, the model gets to look at 1% of the data. So we take our CPC encodings. We pass 1% of the entire data set. So if we had a data set of 100,000 images, we take only 1,000. And we pass those through the CPC encodings and train maybe like a really small model. For contrast here, they have a ResNet 200 trained on the actual pixels. And then we see that a ResNet with 33 layers trained on these CPC features more than doubles the performance, looking at only 1% of the data. And as you can see, as we let the model see more and more data in its supervisory section of its training, this actually scales. So even when both models see 100% of the data, the smaller model trained on the really good contrastively learned features still outperforms a much larger model trained on the raw images. We see 3% better testing accuracy on this data set. The bottom 3 rows are just the ImageNet top 5 accuracy reported, which is just the difference between top 1 and top 5 is like you get it correct if it was one of the 5 highest classes you predicted. And we see this change still scales, 2x data efficiency. In both of these cases, we can do better than a bigger model seeing all the data with our smaller model seeing only half the data. The caveat being that we train on these CPC features or the encodings of our data set into CPC features. Do these results make sense? Any questions before I move on?
Wait, so just to clarify, are the CPC encodings trained like unsupervised on the entire data set, but like after that, it's trained supervised only on 1%, 2%, and so on?
Yeah, good question. So it doesn't even have to be the same data set. So the CPC model that you're using to make your features can be just, we could train it on ImageNet and then give it CFAR and see how it does. And it would probably do pretty well. But yes, to answer your question, the workflow is maybe you take one really, really big labeled data set or unlabeled data set, I should say. You train a CPC model to encode and create features unsupervised. And then you take your data set that you actually care about. Maybe you don't retrain your CPC model at all. You just featurize that data set with your unsupervised CPC model, and then you train a really, really small model with the inputs being the CPC encodings and the labels. So we're training supervised being the actual labels of that smaller data set. So yeah, you do an initial pre-training unsupervised on a big data set, and then you do a much smaller model on a much smaller data set with those encodings as input. Does that answer your question?
Yeah, that makes sense. And also, are these encodings like invertible?
That's a really good question. Yeah, I mean, people have put a lot of work into trying to invert neural networks. That I would say probably not generally, because we're not placing any restrictions on the weights that are learned. So we're not placing any restrictions that say like layer K of the model has to be an invertible map. It can learn some sort of lower rank matrix that actually does change the actually isn't invertible. Now that I think about it, also, typically what you do is, let's say we have a 500 by 500 by 3 image. We're probably not going to want to keep that all around because a lot of that's probably noise. So maybe we actually train CPC to emit a feature vector of size like 100 or something like that. So we're actually reducing the dimensionality throughout the CPC encoding to kind of like the intuition being maybe we remove some noise or something like that. In that case, since there is actually a dimensionality reduction, it's definitely not exactly invertible.
Yeah, that makes sense. Cool. Thank you.
Any other questions?
What is the meaning of invertible? I'm sorry, this might be a bit late.
Yeah, no worries. Invertible in general, if we have a function f, maybe this function is our neural network representing CPC, and it takes in an input x and produces y. So y is the encoding of our input x.
Oh, okay, just like normal invertible.
Yeah, just like an invertible function. Yeah.
Thank you.
Yep. Yeah. Any other questions? Okay, so I hope you go back and read this paper because a lot of the technical detail is hard to convey in a workshop like this. But hopefully the results are pretty amazing to you. Like you can have the size of your data set and actually end up doing better than a bigger model. Pretty cool. So yeah, go back and read it. I've linked it in the slides. Another idea kind of building off of this, contrastive loss to build some code of our data is contrastive multi-view coding. And the idea is that we can leverage multiple views of the data to improve our representations. So views could be different crops of an image, different RGB channels, different lightings, etc. They could be literally different views. Like I take a picture of my computer, then I move across the room and take another picture of the computer. Regardless, different views of data are just, some change in what the input data looks like that maintains the subject. And views must simply contain a common subject. And the idea here behind contrastive multi-view coding is that we want to embed our inputs in such a way that we maximize some similarity score between embeddings of different views. The reason being, like, let's say I had a view of a car from, across the street and a view of a car from across the street, but I moved 50 feet to the left. Maybe I capture some noise in between the two. So like there's a cat in the background of one of the images and someone's, walking in the background of the other. Across the views, though, these are going to be averaged out, and the commonality between the views is the subject of the image. So the idea is that we kind of, through these multiple views of data, can really get a lot of the noise removed from the data by learning to encode them in a creative way. So mathematically, if we have two views, V1 and V2, we want to essentially maximize this score, where F theta 1 is the encoding of view 1 and F theta 2 is the encoding of view 2. And this is a similar thing that I talked about before, is we want these views to be so much similar that they're predictable via a linear map, W. So W is just a matrix, it's just linear regression essentially. We want these views to be similar enough to where we can get them together just by matrix multiplication. And we make a contrastive loss that just kind of does this whole softmax idea that we saw before in contrastive predictive coding. So if we take a bunch of views that aren't matched up, so maybe V1 is an image of a car and V2 is an image of the ocean, these really shouldn't be encoded to anything near each other. And that's what we have here in the contrastive loss, is in the contrastive learning setup, these unmatched views represent noise, and we want the score that we give our representations, e.g. their nearness to each other, to be much higher for correctly matched views as opposed to incorrectly matched views. So two views of the same car, they should be a lot closer to each other in representation than a view of a car and the ocean. And then you can see that kind of graphically laid out here. We have two views of this strawberry. One's in RGB. I think this is in another color space. We encode them into these, latent representations, and we want them to be pretty close to each other. You see here that where they map to in the latent space should lie near each other. And then we have this other representation. I can't actually tell what the image in here is. It looks kind of like a cat, but we see that as a result of this contrastive learning, we want, or we end up with a case where Z2 is actually, or this image of a cat is mapped much further away. So we want like some sort of separability so that we can tell instances of views apart from each other. And what we get here is, representations that remove a lot of the noise that come between views. So they learn to both separate views of different objects and bring together views of the same objects even in the presence of noise. So what we have on the right is kind of the results again. This is a similar thing. This is ImageNet trained with the CMC features. And then all you do is, once again, similar idea, train linear regression or a linear classification model on top of this, like an SVM or logistic regression. And we see how well we can do. And you can see, there's a lot of methods listed here. These are all, I think, unsupervised methods, but you can see how CMC compares to it. The classification accuracy, if we add just one layer, does pretty well, but as we start adding more layers, like if we add just a very small convnet on top of these features, it absolutely obliterates other unsupervised methods. Okay, so any questions here about CMC or CPC?
Actually, for this, yeah, quick question is, like, for this, I know that one method of improving your model accuracy is augmentation. So like with a standard covenant, you just like shift it around. Is this basically just a more explicit way of making sure like the model recognizes that those images are similar?
That's a really good question and a really good observation. I think you could think of it like that. I don't know if I'd go so far as to say like they're exactly the same process, but it is kind of this similar idea of like getting robustness and increased accuracy in your model by giving it enough looks at the same thing such that the noise has to be removed in between them. I will say with augmentation, you're not getting any new information, right? Like you're just taking an image and you're doing something to it, like color jittering it. This is two actually different images. So, in this example, maybe they're in different color spaces, but one thing that the authors also did was like, okay, well, what if we look at like an image taken in RGB and then the other view is like a heat map. And it's just a visualization of like, the literal heat map of what's going on in the scene. And those were the two different views. So in this case, you are adding some information to your representations. It is kind of like an augmentation, except the kind of like denoising is I guess, much more explicit in that you want to match across views. There's no criterion within augmentation in general that makes you match across augmentations in their representations. But yeah, I do think that's a really good mental model to have about this, is like this kind of more general concept of like giving a model more looks at the same data may improve its robustness. Any other questions? Okay. Okay, and then really like this last bit is really short. I think we've been going for a little while now, so I'll kind of just wrap it up. We're right at about an hour. So the idea here is I'm just going to give you like a very small taste of some sort of semi-supervised learning. And the idea is something that we've been seeing throughout this is like unsupervised pre-training. We take a model that we train on a pretext task and fine tune it on the task we want to solve. So the benefits, we can leverage large unlabeled data sets for pretext training, and we only need a small labeled data set for fine tuning. And this is deeply connected with representation learning, of course, because the whole point of the pretext task is to learn good representations for downstream fine tuning tasks. And we want to learn representations that can be generalized to multiple fine-tuning tasks. One of the examples of this in language and specific and sequence modeling is GPT-3. I mentioned it last week when I talked about attention, and I'll show it to you here. I'm not going to talk about actually the unsupervised pre-training approach. I kind of just wanted to show that this is something you can do. So this is, as an intro, GPT-3 generating HTML for, it's generating HTML when you tell it what you want, like in plain English. So you can tell it like, I want a red button, and it'll generate the HTML for a red button. But I'll just show this because I think it's actually pretty incredible. So he's typing, he wants a button that looks like a watermelon. It generates the HTML and gives you this button that kind of, I guess, looks like a watermelon. And he's typing large text that says, welcome to my newsletter, and a blue button that says subscribe. And the text is actually hidden. So you can actually just say large text in red, and it generates the HTML for it. I don't know if you can see that, but he said a button for every color of the rainbow. And the model's running, and it generates the HTML for one button for every color of the rainbow. And he's saying a table of the richest countries in the world with columns name and GDP. Oh, I guess it generated a syntax error, but I guess he's going to fix that. I hadn't watched this far in the video, to be honest. But it actually, okay, so I don't know if you saw that, but it actually encoded some domain knowledge as well and got the, countries right when it was asked to. Let me pull that back up. So all he asked for was a table with the richest countries in the world and their GDP. And not only did the model generate the HTML for that table, it filled in the data as well. And I think this data is actually accurate. But the point I want you to take away from this is GPT is not trained to do this. GPT is trained to learn to represent sequences of text in general, and kind of learn how text is formed and how it fits together. It learns this in an unsupervised pretext task where it's trying to just predict next words in a sentence. And then what people do is, in a very realistic amount of time, they can take a trained GPT pretext model and fine tune it on a task like generating HTML given a description. And you get really, really incredible results just like this. And when I say that unsupervised learning is the future, this is a big reason why. You can train a GPT-3 model to do something like this in only a couple of hours, given one that's already trained on a pretext task. So it's pretty incredible what unsupervised learning can do. Any questions here? Okay, so that's all I had for you guys for the presentation. Hopefully you learned a little bit about, the flavors of unsupervised learning, how we can construct really good, robust representations, and how we can model distributions in an unsupervised manner. And kind of the biggest takeaway from this is how unsupervised learning can really help more complicated supervised learning tasks down the line. So yeah, I hope you guys learned a lot. I'll stop the recording here and hand it over to Anish, who's gonna do the notebook.
Sweet. Thank you, Joey. That was like an incredible presentation. I definitely learned a lot. Cool. So this, let me share the link for this notebook. This notebook is also derived largely from the same class that Joey, that Joey kind of pulled concepts from. You might have to just make a copy of this notebook, just so that no one overwrites the original one and everyone's getting conflicting notebooks. But so I talked to Alexi, and he said that I think for this one specifically, because the concepts are generally very hard to implement, we decided that instead that we'll kind of implement the whole thing and kind of walk through kind of the objective of the notebook, and then make sure that we kind of ask the right questions at each step to ensure that like we have some level of understanding of what's going on. So this won't require you to actually do any coding, but instead just you'll get a feel for running the code, having to look back in the code to answer these kind of specific questions, but ultimately at the end kind of appreciate the power of these autoregressive models and unsupervised learning in general. Joey, do you mind giving me like so I can share my screen just so I can give a quick overview of let me see.
Yeah,
Okay,
you should be able to now.
sweet. Okay, cool. So let me just kind of briefly give an overview as to what the objective of this notebook is. So at okay, let me just start from the top, I guess. So really we start with trying to, model in an unsupervised fashion, of course, one-dimensional data. So in this case, we're kind of given, let's see, like we're given sort of one-dimensional data, and we're actually giving incomplete one-dimensional data, right? So there's obviously some true distribution that represents the real, the real distribution that we're trying to fit, and we're given some subset of that information that we're trying to kind of hopefully model the true distribution. So there are inherently missing values in this training set. And then the way this notebook kind of approaches it is it takes there's two methods with which it tries to fit this distribution. It first does it in a by like negative log likelihood. So it just tries to maximize the likelihood. So it tries to fit whatever kind of in a discrete sense, what the density that kind of best fits the true distribution. And then the second one is sort of a more a nicer looking one, which uses the logistic distribution. So it's a more continuous way of kind of modeling this histogram. But in either case, what we're really trying to do at a fundamental level is in an unsupervised fashion, how can we really fit some model to this one-dimensional data that we have? So clearly here you can see there's a nice mixture of logistic distributions that kind of fit this empirical information that we're given. Whereas in the earlier case, it's a lot more kind of choppy, but it still fits very well. And so once we have this kind of knowledge of being able to fit one-dimensional data, we want to see if we can kind of put two and two together and fit right here a two-dimensional image, right? So here, as I said earlier, right, we have a true distribution, which is like a nice pixelated smiley face. And of course, the training set is kind of like a subset of that, or something that kind of tries to represent the true distribution, but doesn't entirely encapsulate the same amount of information. And from this training set, the question is, can we somehow model, model this true distribution? And so, when we have information on being able to do it in one dimension, we should, somehow be able to kind of figure out in a way that we can model the two-dimensional the data. So what we end up doing is, and again, I don't want to reveal too much because I think it's really useful to be able to go through the code a little bit, but right here, we kind of model each independent dimension using those same techniques that we kind of established earlier with one-dimensional data. And then suddenly, like when you multiply these two together, you get the joint. And so suddenly you get like a good probability distribution over both, the rows and the columns. So suddenly you have a good two-dimensional understanding of the original data. And so, and again, this is autoregressive in that like we kind of account for our own predictions or our own internal understanding of what we've previously predicted for certain rows or certain columns or whatnot.